Okay, thank you. Thank you for giving me this chance to present my work today. So we are going to see and discuss the potentials of X-ray Raman scattering for the study of cultural heritage objects, including like natural and cultural heritage objects. Oh no, what's going on? It's possible. No. Okay. So I'm going to start this talk before we go on with XRS by introducing the specificities of heritage materials. So in general, they are complex in chemistry, and we may have mixtures of organic and inorganic phases, and these components may be different in relative abundance. For example, organics in some cases may be present as minor components. We also have alteration of their original chemistry. They may undergo aging processes or diagenesis processes depending on the context. And to characterize them, we need fine spectroscopic tools. In addition to that, in some cases, we may have multi-scale heterogeneity, meaning spatial variations of the chemical compositions in the objects. So we need as well imaging techniques. If we go with the specific case of paleontological specimens that are quite complex and we want to characterize their chemistry and decipher their original and outer chemistry and understand how exceptional preservation occurs, we often need chemical imaging. If we are looking at the inorganic phases or the elemental characterization, scientists the last decade have made quite advancements in a lot of techniques. So we have rapid synchrotron, X-ray, fluorescent techniques to map at the large scale such fossils. But the question is, if we are looking for organics and if we are looking at light elements, what are our options? Okay, so one technique that has been used the last, 10 years is time-of-flight secondary ion mass spectrometry, or TOF-SIMS. So Lidgren has used this technique to look at molecular preservation of pigment melanin in fossil melanosomes. And the problem with this technique is that only the very first few nanometers are analyzed. If we want to do large imaging, it's difficult because of the surface roughness. We have also scanning transmission X-ray microscopy. Cody had looked at molecular signature of kidney protein complex in Paleozoic arthropods, and this is a powerful soft X-ray technique. So we have the main limitation for the study of heritage objects with this technique is the submicron path of the soft X-rays. So we need ultra thin samples of thickness of 100 nanometers. And this is limiting first because we have to select a specific region to sample, and this is maybe not representative. And we have also the surface sensitivity of the results. Okay, so if we are looking at the carbon KH at 300 eV, this is a penetration length of 100 nanometers. But what if we have a probe of hard X-rays that they can really go in depth in our sample? And that's the case for X-ray Raman scattering. And this is how we can use it non-invasively without any sample preparation requirements to obtain information that it is actually it's an alternative probe of soft X-ray absorption spectroscopy, and we can obtain similar information. We can probe the carbon KH. So in the X-ray Raman scattering process, we have a hard X-ray photon interacting with a core electron, and it excites the electron into an unoccupied state. And for energy and momentum conservation requirements, we have a photon scattered off the sample with less energy. Okay, for our setup, what we need is a synchrotron beam. We have the hard X-rays interacting with the sample. We have a spherical bent crystal and our detector falling in a Roland geometry. Usually what we do is we are scanning the monochromator and we are keeping the analyzer fixed in such a way that the energy difference falls into the edge of our interest, of the edge of the element. And for the carbon is 280 to 320 eV. An important parameter of the XRS process is the momentum transfer. So the way we choose the incident energy and the scattering angle we are going to perform our experiments, it defines the momentum transfer. And also, this is important, these two parameters, the incident energy and the scattering angle, is important to go as far as possible from the Compton scattering background, because we want to achieve a good signal to background ratio. We do not want our X-ray Raman signal to fall into the top of the Compton signal. So maybe before I go on the case studies, if there is anything I can answer.
I think no questions just yet. Thank you, though.
Okay, perfect. Then, okay, so we have our first case study. We have this fossil ant embedded into the amber. The amber is an organic substrate, and our main objective was to identify organic traces to see if this morphological preservation matches the chemical preservation of the resistant macromolecules of this fossil ant. This is a 56 million years old fossil belonging to the Natural History Museum of Paris in France. And we wanted to do that in a non-invasive way. So what we did is we took our samples to ID20 beamline at the SRF, and we performed the so-called direct tomography, the three-dimensional X-ray Raman imaging based on the direct tomography. So when we have an incident X-ray interacting with an heterogeneous sample, the X-ray scattered off the sample along the sample, they will fall in a different area in our two-dimensional pixelated detector. So our spherically bent crystal acts as a mirror, let's say. And we scan the surface of the sample, but we obtain virtual cross-sectional images of the whole specimen. So for each voxel, we collected a complete XRS spectrum. In order to start looking at the chemistry and at the spectrums we obtain into this volume, we started with a model. So we had a sum of normalized reference spectra plus a linear Compton background. So our first reference spectrum was a normalized amber spectrum we collected from the sample away from the ant, and we used that plus the Compton background to fit each XRS spectrum and see how our model is behaving. By calculating the quadratic sum of squares, we saw that it is increasing in the area of the exoskeleton of the ant. So there is something else there other than number. We know that an arthropod's cuticle, at least today, it is an hierarchical composite material and is consisting from the epicuticle. That is, it is rich in lipids and proteins, and then we have the chitin protein complex. And we know that chitin is quite persistent in the fossil record. It is a carbohydrate, but it is not water soluble, and that's the main reason we could identify it in fossils. So we took a reference sample, we bought a chitin sample, and we ran this standard. So we obtained our XRS spectrum, and we added chitin in our model. And we perform again a feed of each XRS spectrum to see how our model behaves compared to the experimental one. And by fitting each voxel, we have the A chitin parameter that reflects the quantity of chitin at each voxel. And by having the spatial distribution at each voxel of this chitin, A chitin parameter, we saw that it is increased in the ventral exoskeleton, and it is decreased in the dorsal exoskeleton. And we saw that in the ventral exoskeleton, we have something similar, a chemical signature that is similar with our chitin standard. And that's not the case at the dorsal exoskeleton close to the surface of the specimen. By plotting the chitin parameter, we could visualize three-dimensionally our ant, and we can see that far from the surface, we have a chemical signature that is close to our chitin standard. And in the dorsal exoskeleton, close to the surface, we have another chemical signature. Okay, so before, I think if there are any questions here.
That's really pretty. What do you think is the final spatial resolution that you were able to obtain with this method, including the decomposition onto the chitin and other spectroscopic contributions?
Okay, so this is mainly restricted to the pixels of the two-dimensional detector. So this is around 50 micrometers. Mm-hmm. If we go back. Oh, sorry, it's not. So this is.
It's okay.
50 micrometers.
I see now. Yes, yes.
There are improvements. We have an algorithm introduced by Alessandro Mirone, Christophe Salle, Simon Huotari that improves the spatial resolution, but and we performed this algorithm in this data set, but at the end we decided to go with the 50 per 50 micrometers.
I see. How long did each? How long did the total measurement take?
It took a lot.
This is Raman scattering, and you need a spectrum at every pixel. A day, 2 days, or roughly how long?
It was a day.
A day. Okay.
If you see here, we scan, I cannot show with my mouse, but we scan, you can see the scanning direction. If I was to repeat the experiment today, what I would do is going and scan, not in the long surface of the ant, but in the short, in the shorter.
Oh, I see.
So in this way, we would have reduced our irradiation time, and still we will probe the whole volume. But I think with time, I don't know.
I see. Okay. Very good. You should continue. Thank you.
Okay, thank you. Let's see. Okay, so the second case study I wanted to share with you is this, the experiments we did in this 20th century collection of Australian plant Exudates. This collection consists of resins, we have polysaccharides, we have different materials, and these can be found today, and they are until today used by contemporary indigenous artists in Australia, and they are also found in ethnographic museum artifacts. So we went this time at 6-2 beamline at SSRL, and we collected high resolution, high energy resolution XRS carbon KH spectrum. And we collected that for different samples coming from different genera, from Xanthoria, Calitris, Eucalyptus, and Acacia genera, different species, different genera. And you can see the different chemical fingerprint that XRS gives. And actually the resolution is really comparable with soft X-ray absorption techniques. We obtain 0.3 EV resolution. And we focused in this area of the edge from 283 to 291. And we decomposed our signal in transitions, in Gaussians that corresponds, its center corresponds to transitions at known functional groups to chemically characterize those samples. So this is coming, this assignment comes from the literature we can find from soft X-ray absorption techniques. Okay, and to make sure that we do the assignment correctly and we correctly characterize those features, XRS features, we also collected FTIR spectrum to have like a complementarity of the characterization. And by performing linear discriminant analysis on this Gaussian decomposition, we could really cluster the different samples based on their genera. And I wanted to highlight here the importance of the energy resolution when we want to collect data at the carbon KH, because collecting with the low energy resolution data cannot give us the same clarity to identify the features. Okay, so in my opinion, XRS can give, like, it has a lot of potentials, especially at least in the cultural heritage field, but there are still challenges to be addressed. So XRS process has a low efficiency. The cross-section of the process is low, so we have long acquisition times. There have been the last decade improvements in the instrumentation, like the two groups that I know, at least at the SRF and at SSRL, they have done a great job in improving the spectrometers and their instrumentation, but still we may have, especially for organics, radiation-induced effects, that they will form new chemical bonds or they will create visual damage in precious samples. So studies has to be made to clarify those aspects. Then when we are looking at organic traces, like when we want to identify organic traces, if in our sample there are heavy elements, we may not be able to detect the XRS signal. Then there is the limitation of the spatial resolution for the direct tomography, so we can achieve like 25 micrometers. There are improvements, as I've mentioned before, from the algorithms introduced by Alessandro Mirone and Christophe Salle, but still we cannot compare it with the spatial resolution of CT, for example. And the last one is the penetration depth that is restricted to the incident beam. Thank you. That was that was it.
Ah, very good. That's very interesting. To begin, we have a question from Adam Hitchcock.
Okay. Great.
Hi. Very interesting presentation. It's really impressive how far along the X-ray Raman technique is developed, and I expect there's going to be lots more improvements to come. Is the beamline that you're using at the SRF open now for after the upgrade? I don't know where that's at time-wise.
Well, I think now they are operating, yes. I'm not a part of the ESRF group, but I think they are operating.
Have you, so you haven't had a chance to use it yet?
No.
Okay. Did you have a sense of how much that's going to change and which aspect of the X-ray Raman technique as applied to cultural heritage or these types of samples will be most impacted by the higher brightness?
By the? Excuse.
Well, the upgrade is primarily going to improve the brightness, right? The ability to focus and to maintain the photon properties over various conditions, let's say.
Well, I think a beamline scientist would be, like especially Christophe, will be the best to answer, but I think that the brightness will improve the long acquisition times. Maybe we could acquire XRS spectra faster. This is what I would say.
Okay, thank you.
I see that Christophe is here. If he happens to be listening right now, Christophe, would you like to briefly comment?
Hi, yes, sorry. Hi, Rafaella. Thank you very much for the talk. We are in shutdown right now, so I had the chance to join. Thank you very much for it. So to answer this question, yes, of course, we're online. We just accepted proposals, and we will also in the round in September. September 10th is the next deadline. How we improved? Yes, the beam. How to say that? I think overall, at ID20, we don't have more photons, but we have better photons. So they're nicer concentrated in a small spot. So it's less than 10 by 10 microns right now. And I think this is partially will translate into the spatial resolution, yes, via the processes that Rafaella described.
Okay, thank you. Another question for Rafaella. What do you see as the best way that the Raman scattering complemented the FTIR in that second study?
Well, excuse me, could you? I was in the. I'm sorry, I was in the chat and I didn't.
So you showed the FTIR and the as a complement or a check on the Raman, and I wanted to understand what their relative merits ended up being for this kind of study. You know, did you need the Raman, or was it a second analytical determination?
Well, for me, what I found useful is that for like assignment of XRS features that I was not really confident to say that, okay, for example, this one, is it a phenol or is it an aliphatic? Like a transition from an aliphatic group, because the energy range overlaps for this transition. Mm-hmm. I was able to go to the FTIR and say that, okay, we have a slide, like a small feature coming from aliphatics, and we have here a signal coming from a phenolic signal. So yes, we can say that it's an overlap of the two transition, and that's the same for the opposite also happened, like for assignments that I wasn't able to say for sure for FTIR, I was able to identify them with XRS.
Okay.
I saw that Uwe wanted to highlight that high resolution spectra was obtained
Uh-huh.
at SSRS.
Speaking of Uwe, he has his hand up. I think there might be something he wants to add.
Yes.
Oh yeah, hi. Thank you, Rafaella. Really beautiful talk. And I just want to, at this point also to express my thanks to Adam, because we, during this project on the resins, we reached out to Adam to help us a little bit with some of the assignments of these 1s2 pi star resonances. So thank you, Adam, for that. I believe that there are two optimizations for these large solid angle Raman spectrometer, right? One way, and that's more the way how SSRL goes. So maybe also a little bit a long question about flux and brightness. I think if you only go for a spectroscopy, you can do very well at pretty much many of the beamlines around the world if you have a good high resolution analyzer crystals in particular. So we use these dice crystals. Their resolution, spectral resolution, is really the key. If you go to X-ray Raman imaging, which is the specialty of Christoph Sahle and other instruments, at that point the brightness, of course, these brightness of the synchrotrons will really help you. And of course, you can also use the instrument what Christoph has been building in both modes. You can use it in a more high resolution spectroscopy mode, where you don't care so much about the spatial resolution, but only about spectral resolution. Or then you can move to this more high resolution spatial imaging mode. So I think that's my take on where the field has been going now with all these new super bright synchrotrons coming up.
Okay, very good. Thank you, Uwe. Peter Botz, you had a question?
Yeah, thank you. First of all, thank you for the talk. That was really interesting. You mentioned that the presence of heavier elements could impact on your ability to detect the carbon KH, and I was wondering what the reason for that is. Is that because of absorption, extra absorption of the X-rays, or because of overlapping edges?
Because of the absorption. If you have a heavy element that absorbs the X-rays, you will not be able to detect the X-rays scattered off the sample due to X-ray Raman scattering process. They will not be able to escape the sample and to detect it.
When going to higher energies, resolve some of that, or am I not understanding the problem?
I think we can go up to 15 kV. This is, I think that's the case.
I think I'll just interject that the problem is that if you go to higher energies, the analyzer crystals become less efficient.
Okay.
And there's a second problem, which is the Compton background gets extremely large when you have a lot of heavier elements present. So both the absorption and the Compton background make it a much more difficult study.
So doing XRS on heavier elements wouldn't be ideal either.
It's been done if you want to study the heavy elements themselves. We have some papers on uranium XRS, for example, looking at very low energy excitations.
The problem comes when you want to detect the carbon KH, like the energy transfer at the carbon KH, but you have the presence of other elements, so you have an heterogeneous sample.
So how would elements like calcium already impact on that? Thinking about cultural heritage materials.
For example, like I have an example in mind. I wanted to study bone black, to study the organic phase of bone black, and because you have the hydroxyapatite there, I couldn't detect the carbon signal. I don't know. I did that with not like the optimal instrumentation. I don't know if I try again today and I try at maybe at SSRL or at the SRF that they have these larger solid angle spectrometers, if I obtain to have a signal after a long acquisition time. But when I did that with 4 crystal analyzers, I couldn't detect the organic phase of this bone black.
With these techniques, another question, what is the detection limit for example, carbon in easy samples?
Excuse, I didn't understand the question.
What kind of concentration, what percentage of carbon needs to be in the sample to be able to detect it?
I cannot be quantitative. I didn't do that. I wish I could answer this question, simplify also my life, but I couldn't. I think more research should be done to be able to give you quantitative numbers.
Thank you.
It's going to be very case specific and spectrometer specific, yeah.
Right. I mean, can I maybe just?
Of course. Uwe, is that Uwe? Yes. Go ahead, Uwe.
Yes. Hi, Peter. Actually, I think Demosthenes has shown at SSRL they can even measure carbon. They measured oxygen and carbon Raman scattering from gas. You can measure very dilute samples as long as there is nothing else in there. That's the problem. The problem is that everything, whatever absorbs X-rays, right, will kill your scattering volume. The question is how many carbon scatters can you access with your X-ray beam, right? And you can have 90% carbon and 10% lead, and you see nothing. You can have 90% hydrogen and 10% carbon, and you see a perfect carbon signal, right? So that's the bottom line. The bottom line is not so much the concentration; it's really how much of the carbon atoms can you reach with your X-ray beam.
Thank you.
Okay, one more question. Tim Hyde.
Hi, thank you. Very nice talk. I'm just wondering what practical measures you would take, particularly in the 2 examples you've shown, to limit any effects of beam-induced effects, particularly if you say you were measuring for one of the samples for at least one day. Can you prove there was no effects, or do you have to just live with it?
Well, for sure I cannot prove there is no effects. What I can say is that also my reference materials were collected in the same conditions. So the radiation-induced effects were the same. If I was repeating this experiment today, what I would have done differently, let's say, is to first collect the data at high energy resolution. So we collected this data with only one monochromator, with the low resolution monochromator to have more flags in the sample. What I would have done today is to also include the second step monochromator at ESRF, the high resolution monochromator. This will reduce the flags going to the sample and also improve the energy resolution of our spectrum. So in this way, I think we would have more, less radiation damage, let's say.
Okay, thank you.
Okay. I think that we've worked through the questions, and I want to thank you for a very well presented talk on an interesting topic. And it's great to see another example of spectroscopies being applied to natural and cultural heritage materials. So thank you again. I will remind everyone the talk is weekly. I admit I'm missing a speaker for next week right now. So if someone knows someone with a great talk that's already ready to go, please contact me. The 6 weeks after that are booked, but I had someone cancel for next week. Well, without further ado, thank you everyone for coming, and I'll stop the recording.